Explanation of supercapacitors, ultracapacitors. What are supercapacitors, ultracapacitors? Supercapacitors, also called ultracapacitors or electrochemical capacitors, are energy storage devices that bridge the gap between traditional capacitors and rechargeable batteries. They can store much more energy than conventional capacitors and charge/discharge much faster than batteries. Think of a supercapacitor like a sprinter. It can release and absorb energy in quick bursts, whereas a battery is more like a marathon runner, slower but longer lasting. How do supercapacitors function? Supercapacitors store energy using electrostatic fields, like capacitors, but with a much larger surface area and thinner dielectric, enabling them to store far more charge. Microscope structure. 2 electrodes, usually made from activated carbon with extremely high surface area. Electrolyte, an ionic conductive fluid between the electrodes. Separator, a membrane that prevents the electrodes from touching but allows ion flow. High-voltage charge storage mechanisms. Supercapacitors use 2 main mechanisms. Electric double-layer capacitance, EDLC. Energy is stored through charge separation at the electrode/electrolyte interface. Purely physical, no chemical reaction. This makes them highly durable. Pseudocapacitance involves fast and reversible redox, chemical reactions at the surface of the electrodes. Common in hybrid supercapacitors. Comparison with battery and capacitor. Feature traditional capacitor, supercapacitor battery. Energy density, low, medium, high. Power density, very high, high, low. Charge time, milliseconds, seconds, hours. Lifespan, cycles, 1,100,000 to 1,500,000 to 3,000. Mechanism, electrostatic plus electrochemical, where are supercapacitors used? Because of their unique properties, fast charge, long life, they are used in many applications. Automotive. Start-stop systems, engines turn off at red lights and restart instantly. Regenerative braking in hybrid/electric vehicles. Backup power in electric steering systems. Battery, renewable energy. Stabilizing power from solar panels and wind turbines. Short-term energy buffer. Energy harvesting systems. Laptop computer electronics and IoT. Memory backup during power loss. Power stabilization in smart meters, cameras, and mobile devices. Factory, industrial, and aerospace. Quick bursts of energy in robotics, cranes, and aircraft systems. Power smoothing and sensitive control systems. Wrench, everyday applications. Flashlights, toys, remote controls, fast-charging models. Smart cards, RFID systems. Pros and cons of supercapacitors. White heavy check mark advantages. Fast charging/discharging. Extremely long cycle life. High power density. Safe and reliable, no explosive chemical reactions. Low maintenance. Warning, limitations. Lower energy density than batteries. They don't last as long. Voltage balancing needed for series connections. Self-discharge is relatively high. Rocket future potential of supercapacitors. Supercapacitors are becoming more relevant in the age of electric vehicles, renewable energy, wearable tech, and IoT devices.